I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Physical. We will briefly reference calculus, but you don't need to know calculus to understand the result. The problems we explore appear in my calculus book, Smith and Minton Calculus, published by McGraw-Hill. If you played a sport that uses a ball, you've probably been told numerous times to keep your eye on the ball. I learned from the excellent book, Keep Your Eye on the Ball by Watson Bayhill, that math has something important to say about this well-intended advice. If you're interested in reading about the physics of baseball, this book is the best. Our basic setup is a batter standing 2 feet away from the middle of home plate with a ball thrown at 90 miles an hour straight down the middle of the plate. If the batter is tracking the ball, there is an angle A formed by the batter's line of sight and a segment from the batter's head to the front of home plate, as shown in the diagram. As you can see in the diagram, as the ball gets closer to the plate, this angle decreases. The question that eventually leads us to a very interesting conclusion is, how fast is that angle changing? Before getting to the answer, I want to say a couple of words about the importance of asking questions like this. Mathematicians as a group can be relentlessly curious, wanting to know everything possible about a situation. Is this question going to lead somewhere? I might not have thought so, but fortunately, Watson Bayhill tried it out. This is a basic Calculus 1 question. If we call the distance from the ball to the plate x, we know the rate of change of x, called the derivative in calculus, but is the velocity of the pitch, and we want to find the related change of a. So here are the calculus details. From the triangle in the diagram, the tangent of a is x over 2, so a is the inverse tangent of x over 2. Computing derivatives, we get a prime equals 1 over 1 plus x over 2 squared times x prime over 2. If you had calculus, were you ever expecting to use the derivative of the inverse tangent for anything? If the ball is thrown at 90 miles an hour, we convert that to 132 feet per second because the 2 in the equation comes from the 2-foot distance. We need feet and not miles. And then substitute in for x prime. We have a prime equals negative 66 over 1 plus x over 2 squared. Now, the larger x is, the smaller in absolute value this is, and its largest magnitude is when x equals 0, putting the ball at home plate. The maximum magnitude is 66 radians per second. To track the ball all the way to home plate, then, the batter's gaze must rotate at rates up to 66 radians per second. Now, to be honest, a lot of traditional calculus problems end here, with a correct calculation that is almost meaningless. Here's where this one gets interesting. Human beings can only accurately track moving objects at rates up to 3 radians per second. 66 radians per second is way beyond our abilities. It is impossible to keep your eye on the ball. So we now have another question for the calculus problem. Where is the ball when the rate of change reaches that human limit of 3 radians per second? Well, you can set a prime equals negative 3 and solve for x, or just use the graphic from the app we wrote for Calculus Lab to find out that humans are going to lose the ball when it is about 9 feet away. So what do batters actually do? Watson Bayhill put eye-tracking headgear on several professional batters to find out. They all track the ball to about that 9-foot mark, so actually keep your eye on the ball is really good advice. From there, one of 2 strategies was used. Some batters maintained their 3 radians per second rotation, falling behind the ball but keeping a steady eye movement. The more common strategy, though, was to jump their gaze ahead to where they thought the ball would cross home plate. This way they could see the ball and bat contact, or lack thereof, and use that information to improve future predictions. Can we apply this calculation to other sports? Well, absolutely. The only modifications you need to make are to change the 2 and the 132 for the distance and the speed. In tennis or table tennis or kids softball, the assumption that the batter is 2 feet off to the side might not be correct, and the ball might be coming at speeds much slower than that 90 miles an hour, which leads to another simple follow-up question that you could tag onto this problem. For what speeds could the batter follow the ball all the way to home plate? Substitute in a prime equals 3 and x equals 0 and solve for x prime to get 6 feet per second. That's about 4 miles per hour. So even at very slow ball speeds, anything above 4 miles an hour, keeping your eye on the ball the entire way is impossible. Our odd little calculus problem ended up leading us, through Watson-Bahill, to a surprising and deep bit of baseball knowledge. I love knowing this result. But to be honest, for some of the coaches that my children had in sports, this is something that I kept to myself.